So let's now discuss rotation about a fixed axis. Here I have a rigid axis. This is on, say, let's just say the z-axis to make it simple to discuss. And the dotted outline is our rigid body, and then I have a circular cross-section that, for right now, let's just say it's parallel to the xy plane. Doesn't need to be, but say it is. So I'll define an angle here that I can create in a direction, maybe this way, of theta is my angle. And then if I have a change in angle, that will result in a d theta for us, small change in angle. So our angular displacement is d theta. Okay, well then if that's the case, I can define an angular velocity, or the way that this thing is spinning about this axis. Call it omega, and omega actually has a direction and will point in this direction if we are going with a right-hand rule. So our angular velocity then is omega equals the rate of change d theta dt. Well, I can continue with this process and come up with an angular acceleration. And again, that will rotate about the axis that we're rotating about. Now it could be in a direction opposite to omega if it's decelerating, but if it's accelerating, it'll be in the same direction, and I'm going to draw it in the same direction as omega, and it would also be represented by its own vector alpha. Also, we can think of d theta as a vector in this direction too, because as you rotate from here to here using the right hand rule, your thumb points in the z direction. Okay, so coming back here, we have alpha, our angular acceleration, is d omega dt, which can be taken further as the second derivative of theta with respect to time. Finally, so we have these differential equations that are real similar to what we had for our rectilinear situation. And because of that, we could also play around with these like we did before and derive this guy, alpha equals omega d omega over d theta, which is analogous to acceleration equals v dv dx. And solving these relationships with constant alpha will give us some relationships that should sit very well with us, where we have omega equals omega naught plus alpha t. So we got that from alpha equals d omega dt. So we integrated alpha dt. Alpha was constant. We can pull it out to the front. Alpha dt equals the integral of d omega from omega 0 to omega, and this was from 0 to t. And of course that'll give us that relationship. And we can pull up these other expected equations from separating variables and solving the differential equations above, just like we did in chapter 12. All right, so let's now look at velocities and accelerations. So around the circle here that we're heading, we'll end up with a velocity here, tangent to the circle, and some distance r, at some distance r out from the edge, then that velocity equals, well, we can think of this actually as a, let me move this r, we can think of this as we look at a situation where we have an incremental change. If we look at the incremental change in the arc length, then keep in mind that, make some room here, that the arc length equals r times d theta. So if this is some angle d theta here, and that's a distance r, which I'll put in red. So this is r in red. Then, of course, we can take the derivative with respect to time of this. And since r is constant, we end up with d theta dt. So this is essentially saying our velocity equals r omega. And that, of course, is worthy of a box. So that's kind of a scalar representation of what's going on. Let's look at more generally, a more general case. So we have our rigid body rotating about some axis in space. We can look at a point again out here, and we can draw a position vector to that point. And in fact, we could draw a position vector, I'll call this the most general sense, from any point on this line of axis, the axis line. And I can come up then with the velocity here, a relationship for the velocity vector, and that vector is going to just be omega cross r p. So if you use the right hand rule, you'll see that crossing omega so omega points in the z direction, and we cross that with rp, for example, we get a we get the vector tangent to the point here. And we could also do the same thing with r, if you have r. Now recall, when you have a particle circling a point, you have a tangential acceleration vector, and you have a normal acceleration vector, and these, of course, add to represent the total acceleration, which usually points inward of the circle you're rotating around. Now, our tangential acceleration is the derivative of the velocity with respect to time, and if you look above, you'll see that we can replace that with the derivative with respect to time of omega times r, which, since r is constant, will result in the derivative of omega with respect to time times r, or omega dot r, or we have a name for that, we call that alpha, our angular acceleration, r. This is our acceleration in the tangential direction. Okay? And if you recall, the acceleration in the normal direction we said was v squared over r, which is going to equal omega r squared, since that's the velocity defined above, over r, which is omega squared r. That's our normal acceleration. Another way of looking at it in terms of scalars. course, we have a more general representation of all this with vectors. And again, we'll want to draw a position vector from somewhere on this axis to this point. And we know that the acceleration equals the velocity with respect to time, derivative velocity with respect to time. So that's going to equal the derivative, according to what we've discovered already, of velocity can be represented by omega cross rp, which equals the derivative of omega with respect to time cross r plus omega cross the derivative of rp with respect to time. Well, then our acceleration just equals, this is alpha cross r, so our angular acceleration plus this is omega cross, and drp dt we found earlier was omega cross rp, so it's omega cross rp. So these are for our tangential and our normal acceleration. And the acceleration in the tangent direction again equals this alpha cross rp, which is in the direction of the velocity. So it's either going to be in the positive direction it's either going to be in the same direction that a velocity is occurring, or the exact opposite direction the velocity is occurring, in case you have deceleration. Now for the normal acceleration, just to show how it works, we know that omega cross rp is in the direction of the velocity here. So imagine this is a circle. And then we know that, oops, let's not use that one. Let's use this one. We know that omega is in this direction, or if it's rotating the other way, it'll be the other direction. But regardless, omega cross r, then with the right hand rule, will create the vector pointing towards the center. And that's in the normal direction. So the normal acceleration points in the negative r direction, or minus r. So because of this, we can think of some scalar simplifications with the normal. So we can say that an equals essentially omega squared times r, but in the negative direction. Actually, let's not do it as a scalar. Let's do this as a vector. Now this is a radius, the circular radius, and not just any radius, rp. So that's not rp. That's the actual radius here, r. Where, if you recall, this is the axis of rotation. rp was any general position vector. So we can represent acceleration by the tangential and normal acceleration with alpha cross r minus omega squared r. And again, this is r, not rp.